going to present the methodology behind making the transition from discrete shot records to continuous wavefield. The outline of the presentation is as follows. We'll start with an introduction, then talk about the conventional versus the proposed seismic method, then go through the processing methodology before summarizing. So the proposed seismic method is utilizing continuous source and receiver wavefields. We call this method E-seismic. The methodology will be described and illustrated with synthetic data examples. We started this research project in early 2014, and it has been funded by the Research Council of Norway, Equinor and PGS. So moving on to discuss the conventional versus the proposed seismic method. What is unique with the proposed method is that continuous wavefields are treated over the full time length at once, in contrast to the conventional seismic method where records are split up into limited lengths. The method requires continuous recording of seismic data. This has already been an industry standard for a number of years. Motion, depth variations and so forth are treated on a continuous basis to make sure that a continuity is maintained in the data. Listening time is not needed with the method. With the conventional seismic method, if sources are actuated with short time intervals or if multiple sources are operated simultaneously, a deblending is needed in order to construct independent shot records. With this method, we treat the entire wavefield as one large wavefield, so deblending is not needed. The source may emit signals continuously while moving. Band-limited white noise is the ideal source for this method. So moving on with the benefits. In terms of operational benefits, there are reduced sound pressure levels because we can spread the emitted signals out in time. There are no vessel speed limitation caused by the method because we simply record continuously and emit signals continuously while moving. The method can be used with air guns as well as marine vibrators or any type of source. In terms of data quality, less edge effects are imposed by finite record lengths. The low frequencies will benefit from the long records, and the spatial sampling of common receiver gathers can be improved, as will be discussed later on in the presentation. We can potentially also improve the cross-line sampling of source positions. So in addition to the operational benefits, the main objective with the method is to improve the spatial sampling of source positions. So moving on with the processing methodology. We take the data through the following pre-processing steps. The first thing we do to the continuous data is to correct for the sensor responses. Then we attenuate the direct arrivals. The next step is noise attenuation. And again, the noise attenuation benefits from the long continuous records. Following the noise attenuation, we apply a receiver motion correction. And then we do a wavefield separation on the receiver side. The equations we used for the wavefield separation is per standard methods. The only difference is that we do it to the entire continuous record in one operation at once. Finally, we do a deconvolved wavefield emitted from the source. In this presentation, we will focus on the receiver motion correction and source wavefield deconvolution. Before we go into describing this further, we will show an animation illustrating the physical experiment of seismic acquisition. The green and yellow line illustrates a streamer. The red circle illustrates a source. The blue triangle and the black dashed line illustrates a stationary receiver position. If we start this animation and you focus on the left-hand side of the picture, you will see as soon as the streamer is in the position of the highlighted receiver position, we start recording live data in that receiver position. As soon as the tail end of the streamer has passed through the location, we stop recording in that location. The temporal length of the live data we record in each stationary receiver position depends on the streamer length and the vessel speed. If the streamer length is 8 kilometers and the vessel speed is 2 meters per second, we record 4,000 seconds of live data in each stationary receiver position. The dark gray highlighted area shows the received wavefields in the position where they were received. If we now play this animation again, look on the right-hand side, you will see that when we start recording in the highlighted receiver location, the source is close to that location, and it's moving away from the receiver location as time goes on. This means that the traces in each receiver location will typically have the strongest amplitudes in the beginning of the trace because the source is closest to the receiver location, and they tend to decay as a function of time. But this is obviously dependent on geology. You will also see on the right-hand side is that if the source is emitting signals continuously while moving, we get an incredible sampling of source position along the source trajectory. This means that we can choose in processing what spatial sampling we want to output in the common receiver gathers, and these common receiver gathers are fully anti-alias protected. So now we will talk about the receiver motion correction. On the left-hand side, the blue triangle illustrates a continuous record. The temporal length of this record is the length of the sail line, so typically some hours long. The width of the blue triangle is the streamer length. In the receiver motion correction, we put the data samples into the locations where the receiver was at the time when the signal was received. And we end up with this large data matrix shown to the right with the signals going down the diagonal. The yellow line represents a stationary receiver location, and the red dashed line represents the location of the source as a function of time in front of the streamer. What we do in the source deconvolution step is loop over each of these stationary receiver locations and deconvolve the wavefield. So in the source deconvolution step, we perform this on individual receiver traces. Individual continuous receiver traces are transformed into common receiver gathers in this operation. In order to do this, we need to know the emitted wavefield from the source. The entire wavefield that can contribute to a receiver position is determined based on the emitted source signals as a function of time, and the position of the source elements as a function of times. These times and positions are relative to the times and positions of the receiver trace. On the left-hand side, we see a synthetic common receiver trace simulated with a source emitting Gaussian noise continuously. On the right-hand side, you see the emitted source wavefield. And what we do in order to build this source wavefield is entirely equivalent to what we do on the receiver side. We put the signals, emitted signals, into the position of the source element at the time when the signals were emitted. And we end up with this data matrix with the signals along the diagonal. The main challenge with deconvolving a multi-dimensional source wavefield from a one-dimensional receiver trace is that we don't have any angle information in the receiver trace. The source wavefield we can represent in frequency and horizontal wave numbers, so we know what is emitted as a function of angle. But on the receiver side, we can do a Fourier transform, but we have no horizontal wave number information. In other words, we have no angle information in the received wavefield. Therefore, in the source deconvolution step, we consider all possible source emission angles. By doing so, we are guaranteed to put the signals in the right places, but we also put signals in incorrect places, causing noise. And that is what we see in the middle of this image, the first deconvolution result. We can see how the reflectors are focused into the correct positions, but we also see some noise surrounding it because we don't know the source emission angles. Therefore, we have implemented an iterative method where we extract coherent signals that we are sure of is related to the response of the Earth. We model the contributions of these extracted signals to the receiver trace. On the right-hand side of this slide, the blue curve is the original receiver trace. The brown curve is the modeled contributions of the extracted signals we can see to the very left. And the yellow curve in the middle shows the difference between the original receiver trace and the modeled contributions from the extracted signals. That we call the residual receiver trace. We now repeat the deconvolution step on this residual receiver trace, considering all possible source emission angles. And we end up with the receiver gather shown in the middle of this slide. What we see now is that the remaining signals that we haven't extracted yet are showing up where they should. But we also see that there is a lot less noise that we spread out compared to what we saw on the previous slide. The reason for this is that all the signals we have extracted, we don't need to spread across all possible source emission angles, so they no longer will produce noise. This means that we now can extract even more signals from these new common receiver gathers. And we can model the contribution from these new extracted signals, creating a reduced residual. And we continue these iterations until we are no longer able to extract coherent signals from the residuals. In this particular case, it stopped after 4 iterations. Then we were no longer able to extract coherent signals from the deconvolution results of the residuals. At the very end, we add this last deconvolution result to the extracted signals to make sure that we don't lose anything. On this slide, we can see a comparison between the final deconvolution result on the left, the side result in the middle, so that's essentially the Earth model that was used to create the receiver trace to start with. And on the right-hand side, we see the difference between the reference and the deconvolution result. If the source is designed such that it's emitting a white wave field in the crossline direction, we can also solve for multiple sources in the crossline direction. In this case, we have simulated the receiver trace with 6 sources and with 100 meters separation. Each are emitting Gaussian noise. And we can output 6 common receiver gathers from this single receiver trace. So to summarize, the seismic method utilizing continuous source and receiver side wave fields have been introduced. The method can handle sources that are continuously emitting signals while moving. A source emitting band-limited white noise would be the ideal source. The environmental impact of marine seismic sources can be significantly reduced because we can spread the signals out in time instead of emitting short impulses at distinct points in time. The acquisition efficiency can be improved because we can increase the vessel speed. There are no vessel speed limitations caused by the method as such. In addition, if we spread sources out wide and we increase the number of sources cross-line, we can also improve the acquisition efficiency. We would like to thank Equinor for their support during the project, colleagues in PGS for their contribution, and PGS for permission to publish this work. Finally, I would like to thank you for watching this e-lecture. If you like this presentation, please visit the EAGE YouTube channel for more e-lectures.